The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Greetings, programs, and welcome back to Element 14 Presents. Matthew here, you there, coming to you live and direct from good old Shop Sweet Shop. Yes, after several months in quarantine, back in the saddle and back ready to ramp production up here once again, at least for the time being. Now, when you've been under quarantine for several months, you almost can't help but think about the passage of time, and of course how we measure time. And that brings us around to the rite of passage for every good hardware hacker out there, the humble DIY chronometer, or clock if you don't want to be fancy about it. Now, what I love about the DIY clock is that there's so much room for creativity. There's so much room for different implementations, different ways to display the time. It's a nice empty canvas where everybody kind of puts their own little spin on things. Now, you may have noticed from my preferred wardrobe choices that I'm a bit of an aficionado of color. So that's what I'm going to do with this project. I'm going to build a clock that displays the time using various shades of color. So grab your crayons and let's get started.
Amazing hacks. Inspired designs. Each week, Element 14 Presents brings you innovative projects using electronics, engineering, and more.
Now, when we're coming up with a clever way to display time, the first challenge is really just converting out of the hexadecimal number system, a base 60 number system, that we use to measure time. You may have seen those binary clocks that take the time and convert that into a binary notation and display that on a grid of LEDs. But with color, it's a little bit different. You see, there's two main ways to notate color information. There's the CMYK method, and then there's the RGB method. Now, CMYK is mostly used for print, so we're not really going to mess around with any of that. We're going to focus on RGB. Now, an RGB value is a 24-bit number that assigns 8 bits, or 1 byte of information, to the relative intensity of each of the primary colors of light, red, green, and blue. Now, if this is all new to you or you need a refresher, there's plenty of information in the show notes at the Element 14 community at element14.com/presents. There's a link down in the doobly-doo to take you right there. Anyway, instead of using 8 digits of binary notation to indicate the value of red, green, and blue, we can do that in 2 hexadecimal digits. Thus, we can convert 2-digit hour, minute, and second values into 2 hexadecimal digit red, green, and blue values and have a unique color representing each hour, minute, and second of the day. Now that we've learned the basic operating principle of the thing, let's take a look at the design. Please excuse the crudity of this model. I haven't had time to paint it or build it to scale. But essentially what we're looking at is a box with a color TFT screen in it that's going to be driven by an Arduino. And then over here, maybe off to the side, I haven't quite decided how I want to arrange it, but I want to have an array of those 14 segment, like starburst style LED displays to indicate the red, green, and blue values, or, the hour, minute, second values, essentially. And then on top, a couple of buttons maybe to set the clock. So to build this thing, here's kind of our little block diagram. We've got the Arduino here in the middle, of course, power coming in from this side. But to keep time, we're going to build a real-time clock module, and that will help regulate everything. Down here, we have the TFT LCD that's going to be driven by an RA8875 driver board. And then up here, we'll have our starburst display driven by something like a Max 7219. Now, the 7219 can only drive up to 64 individual LEDs. So I can't truly drive 6 14-segment displays, but I only need so many segments, maybe 10 each, in order to get the letters A through F plus the 0 through 9 digits. So shouldn't be too much of a problem. A little jiggery pokery, I won't light up all the segments. Anyway, that's the plan, sticking to it. Now let's get to prototyping. First things first, minimum viable product. I need an Arduino that tells time. So I need to write a quick little sketch that'll do all the basic clock functions on the Arduino, and then output that time display to like a 1602 character display, just a serial interface, super simple. And then I can take that idea and then expand upon that with like the starburst displays and the screen and all that good stuff. So let's get that started first. Okay, groovy. Now we've got ourselves a basic clock that we can set the time, we can see what time it is, everything going well, as long as we still have mains power. So we're going to need some way to keep time in the event of a mains power failure. So let's add a battery backup RTC module. Okay, this is the heart of our RTC module. This is a DS1307 Plus real-time clock, which is essentially just an 8-pin DIP package IC with a little bit of RAM in it, and it connects to an oscillator, and that provides essentially a perpetual clock calendar system as long as it's got power, which is really cool because it has really low power consumption, and like a 2032 coin cell can run this thing for like 10 years, so no problems there. It's a good, solid battery backup solution for a clock. So let's take a quick look at how we would wire this into our circuit. Okay, as you see, it's a pretty simple wiring job. We have X1 and X2. It's our connections for our crystal oscillator. So we're gonna have our 32.768 kilohertz crystal connected there. Right here is the voltage input for our backup battery, a coin cell, probably a 2032. And then of course, right here connects to ground. Up here, we've got our 5 volts in from the Arduino. This pin outputs a square wave. I'm going to skip the square wave timing, and I'm going to connect the data line here. And this is a two-way data line. I'm going to connect it to the Arduino on analog 4, and then our clock input from the Arduino on analog 5. And we'll have that, and that will create our little real-time clock module. So let's get this wired together. Okay, so open up the serial monitor, and here we go. We've got a just a running tally of the time, essentially. And check this out, This is the coolest part. So I can take that off. We ended at 43:54, and we're gonna give it like maybe like another 10 seconds. So we reopen the serial monitor, reconnect, and we're still going, 44 and change now. So like 10 seconds have passed, and it's 10 seconds later. Okay, so I have a clock. I have a clock that outputs to an external display. I have a clock that outputs to an external display and has a battery backup real-time clock module for fail-safe. The next thing I need to do is transition from the 1602 LCD over to the little 14-segment starburst display, so I can get that really cool like retro vibe going on. And then I'll be ready to work on the other side of this project.
Hi, I'm David from Element 14 to the Electronics Inside. Join me as I tear down toys, tools, appliances, modern, vintage, classics, and even some new releases, just to find out what's inside.
Now, I need to convert from the 16:2 character display over to something like this alphanumeric 14-segment LED display. The problem is, it requires 18 pins just to fire 2 LEDs, and I just don't have that many pins available on the Arduino, especially since I have to have 6 of these, well, 3 of these guys for 6 digits. Okay, I've got this first unit wired up, and I just wrote a simple variation on the blink sketch that just cycles through each of the pins just to turn it on and off real quick. This is a common anode LED display. It's a little bit backwards from what I would normally work with, like a common cathode. So you got to wrap your head around it that on is off and off is on. It's confusing, I know. So there's got to be a little bit more efficient way to do this, and that's where my LED driver IC comes in handy. This is the Max 7219 LED driver chip. This is a little bit of a weird application for this. Normally, what you would use this for is to drive like an 8x8 LED matrix or up to 8 7-segment displays. It's not really set up to drive 14-segment displays. Let me get this thing wired up and play around with it and see if I can get this working just the way I want it to. Okay, so ran into a little bit of trouble when I went to wire this thing. You see, the 7219 is a common cathode LED driver, and the 14-segment displays that I'm using are common anode. This is a common anode LED display. So that presented a little bit of a problem. Now, obviously I can just wire the whole thing backwards. Now that's fine. Now, compounding that problem, when you wire something backwards like that, everything shifts 90 degrees. Your rows become columns, your columns become rows. That can present itself as a problem. The library I was going to use, it's all set up for common cathode. So I'm gonna have to do a little bit of jiggery pokery in the code to get it to work with this display, this setup. And everything should be okay at that point. Now, I really only need 8 of the 14 segments. The normal figure 8 7 segments, and then this one down the middle, this vertical piece down the middle to make letters like Bravo and Delta. So what I'm going to do is I'm going to map the decimal point that I would normally have on a 7-segment display. I'm going to map that to this vertical piece, and so we'll have that working. So instead of trying to map out every single segment as a combination of segment and digit, I'm just going to do segments, 8 segments on a digit and call it a day. So it would be a lot easier, a little more straightforward, much easier to code. All right, awesome. So now I have my little hexadecimal counter on the 14-segment display. So yes, I'm so excited about this. Yeah, as you can see, the B is a little bit not quite the same because I have both of those segments lit up because that's the easiest way to do it. It's a small price to pay for having it work easily the first time. So now I have my hexadecimal display, I have the counter, I just have to wire in the other 4 digits and figure out exactly how I want to subdivide 24 hours into 16,700,000 blah 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 clock ticks. So that's going to be something I'm going to work on in code down the line. One really cool thing that I really like about this driver that I don't think I mentioned before is that it's only using 3 pins on the Arduino, and the library that I'm using allows you to custom set those pins very easily. So I can pretty much do whatever digital pins I want. That gives me a lot of room to work with because I need the actual I2C interface to interact with the real-time clock because I don't really want to have to rewrite that library as well. So this is very convenient. I can just redefine the pins as I need to, and then I've got plenty of pins to work with to do the next part of the project, which is the nice little screen. And let's get that set up. The very last module I have to put together before I, well, put everything together is I've got to find a way to display the particular color for whatever the hexadecimal translation of the current time is. I need to put that color on this here screen. So in order to do that, I'm going to need a way to drive this screen from a microcontroller, and I'm going to be using this RA8875 driver board from Adafruit. It is a SPI serial parallel interface driver board for like a 40-pin TFT screen. It's built around the Rayo RA8875 chip, which can drive up to like an 800 by 400 display. It's got a few other niceties on here. It's got backlight control. It has a regulated power supply, so you can run 3 to 5 volts in nominally, and it will also regulate 3.3 volt out in case you needed that for like a separate touchscreen controller that Adafruit also uses. So let's go ahead and get this wired up and make sure we know how it works, and then we'll be able to incorporate it into the project later. Okay, so it's a pretty simple wiring schematic, and I'll put a copy of this in the show notes in the doobly-doo. But essentially all you're doing is just connecting power, ground to their respective pins on the Arduino, and then you're connecting the SPI interface to their respective pins on the Arduino as well. So really the only pins that are mandatory are 11, 12, and 13, which are Mozzie, Mizo, and clock respectively. The rest of the pins, the interrupt, chip select, and reset pins, can actually be assigned in the sketch itself. So we're using the hardware SPI interface, and we're redefining some of the other pins in software. And then of course on this side we just connect our 40-pin ribbon cable up to the screen. Now let's upload the sketch and take a look at what we got. All right, let's see what we get. Ooh, got something, got colors. Ha ha! There it is. Okay, fantastic. Now I have a working screen module, so I can attach this to the other modules, bind it all together with some code, and then shove it all into a custom case, and I think we're gonna be done. All right, so here it is all assembled. Now, the case doesn't look like much. It's not supposed to. It's very plain because I want to draw the attention more to the screen and to the numbers along the side here. And of course, you'll have your red, green, and blue values that correspond to whatever hours, minutes, seconds there are in the time. So let's go ahead and plug this thing in and get it running. There we go. And now here we are running. Now this is of course taking away the seconds. It's 255 seconds in a minute in hexadecimal time. This will tick up over the course of an hour, and then this will tick up over the course of a day. 255 minutes in an hour, 255 hours in a day. So as this ticks up, you see the screen get bluer and bluer, and brighter and brighter blue. So that is as this value is rising, this blue gets more and more saturated. And over the course of an hour, the green will saturate more and more, and then over the course of a day, the red will saturate more and more. All three of these numbers will rise over the course of their respective times to the point where at 23:59:59 in duodecimal time, this will be white. The screen will show FFFFFF and all white, and then at midnight, as it rolls over to 0, it goes back to black. So that's that. Now setting the clock, we're going to flip this up to the set position, and then we have an hours set and a minute set. And this is actually going to show us in duodecimal time what the hours and minutes are. So if we want to set it to the current time, Okay, so it is 21:27 current time, which I can actually, I'll bump that up to 28 just for the sake of arguments. You can't set these seconds because there's really kind of no point, because you just flip that. It's a little buggy sometimes, but that's why I have that subroutine that will check the current time on the RTC and then adjust the hexadecimal time appropriately, because there is going to be some time drift. That's all the time we have for this episode. Question: have you ever built a clock or come up with some clever, novel way to display the time? Let me know in the Element 14 community at element14.com/presents, link in the doobly-doo. While you're there, you can check out the contests, the road tests where you can get free stuff, and the myriad instructional guides. And if you are so inclined to improve upon this project, you will find everything you need, including the plans and the Arduino sketch as well. My name is Matthew, and until next time, remember, it's okay. It's just a prototype. Rally ho, y'all.